Hi everybody, my name is Tom Giersz and I work for Nichols Boreholes. I've been working for the company in renewable kind of sectors for the last 11 years. So kind of know a bit about ground source heat pump, air source heat pumps and water wells. That's what our company do. But I'm not going to bore you with the water wells or any other stuff. Just we are going to focus on ground source heat pumps. So Simon, do we see our screen?
We can see your screen,
Yeah,
yeah.
okay.
Yep.
So just a quick kind of brief kind of explanation how the heat pumps are working, and that they are working kind of in similar way, no matter if it's we're extracting water from the well or from the closed loop boreholes or from the river. We are taking the heat via the glycol from the boreholes and providing the heat to evaporate inside the heat pump, which you can see on the left-hand slide, kind of on the top. And then gas, which is inside the compressor or kind of inside the heat pump unit, the heart of the unit, is taking the heat away from the glycol. Gas warms up, is then compressed and warms up, can warm up even to 100, 110 degrees, depending on the model of the heat pump, depends on the type of refrigerant. The temperatures can vary. And then when the gas gets hot, it transfers the heat via another heat exchanger to your heating system or hot water system. And then based on that, gas drops the temperature, goes through the expansion valve, is decompressed, and the cycle goes around in a circle all the time. So that's kind of the main kind of, and all the heat pumps, no matter which manufacturer we are talking about, they are working kind of similar way. And they've got different type of compressors inside and expansion valves, but the kind of the whole logic is very much the same. Newer heat pumps can now provide also cooling. Some of them have got this option built in, and some of them you have to install additional heat exchangers outside. But yeah, that is now kind of the technology is now moving forward, and that is becoming more and more popular with the properties. So as I said earlier, we've got few different types of technology. So kind of it's the same heat pump, but you're extracting the heat from different sources. So in top left picture, you can see those are the boreholes, and you can see the borehole tops and then horizontal pipes linking the boreholes with the manifold. So this is considered as a closed loop system. And depending on the demand of the property for the heating, hot water pool, you might have from one borehole to 50 or even more. So that depends on the demand. And the picture on the bottom, that is open source, open loop system, where we are extracting water from the water well. There is a pump in the extraction or abstraction well. We are pumping actual water from the aquifer into the heat exchanger unit, and the heat exchanger takes the heat from the water, and the water is then discharged to discharge well. So that's an open loop system. We can also do system where we are extracting a river from a lake, pond, depending on the size. And that is very common as well if the properties or, commercial properties are near the lakes, London, Thames River, that is quite common as well, because that reduces the drilling kind of aspect of the system. It involves a bit more environmental agency in the permit side, but it works out potentially slightly better. And then hybrid options, which combine ground source heat pump with air source heat pump, gas, oil, or solar. So that is, let's say, if we've got all the properties and you cannot upgrade the radiators, or the flow is required or is too high, or required to be too high for the heat pump to manage this, you might say at 5 degrees outside, we are going to switch off the ground source heat pump unit, and we'll then move on to oil or boiler. But that is oil or gas. But that is still more efficient, because majority of the time the temperatures are above that, let's say, the bivalent point. So you're still kind of improving efficiency of the property. the next thing I'm going to kind of discuss with you is the design of the borehole system. So to do the design, depending on the size of the property and kind of the whole project, in some cases, we would recommend doing thermal response test, which is TRT, which gives us really good information about the geology, the aquifer, and kind of the thermal conductivity of the borehole. So, but we would recommend this in the larger commercial or large domestic properties where we've got multiple potential for multiple boreholes, because doing this can reduce the number of boreholes quite significantly, and then reduce, of course, the capital cost of the system. So that it kind of we could do this first, and the borehole which is used for the thermal response test can be used for the future kind of number of boreholes, so that can be included in the normal later design of the system. So, and to do the design of the system, we need a full heat loss assessment, so accurate building demand profile for heating, cooling, hot water. We then assess the ground conditions, geology, thermal conductivity, groundwater presence, and any other reports that we've got available. Some of the reports we can obtain from different sites, like BGS site, where we can look, and it's available for everybody. You can look at the local geology and local boreholes, because all the drillers should report all the boreholes they are drilling. So looking at those reports, we can then obtain kind of information about the geology, actual geology, and at what depth we hit the water. So we then know, is the geology saturated, is it dry? And then based on those information, you would then design the depth of the boreholes. So yeah, we would normally do them between 100 to 200 meters, but that depends on the load and geology. So if we know we are in chalk, we might drill boreholes deeper because they are more efficient. But if we are going to we know we are drilling in sand or running sand, we might then avoid this area because they are a bit more, not dangerous, but they can provide a bit more problems with the sand collapsing. And if that's the case, we might have to, driller would have to case the borehole to a certain depth to reduce the risk of collapsing and be able to insert their probe to required depth. And then after that's been done and grouted, then the casing comes out and the borehole is, collapses and it's fully kind of working. So yeah, that depends on the size of the project. You might drill one borehole up to 50 or more. That's, we've been working on the projects where we are looking at 300 boreholes. So yeah, it varies depending on the demand of the property. What's important is also kind of knowing what kind of grout and backfill you are going to use in certain geology. So if you've got, let's say, clay and it's dry, you would probably fill this with a grout which will fill and expand inside the borehole to remove any air gaps and fill the borehole and provide good contacts with the geology surrounding the probes to transfer the heat from the geology into the probes. So, but if you are going into the chalk, which is well saturated, we'll probably fill the borehole with some sort of shingle, and which then that allows the water to flow through the shingle, and water provides great kind of energy input, and that provides good transfer. So that's kind of improves the efficiency of that section of the probe. And then, so that's kind of the main thing. And the top part of the borehole is normally filled with some sort of grout bentonite to seal the borehole, so any of the surface water cannot penetrate through into the boreholes and damage or kind of provide any kind of debris or to the boreholes or kind of damage the aquifer.
Tom, you mentioned you've worked on projects with up to 300 boreholes. You probably cover this, but I mean, what does that represent in terms of energy demand? What type of building would require 300 boreholes based on
Well,
the amount of energy that demand that they have, and how would that then relate? Is there a sliding scale? How would that relate to, say, a large house or whatever? I mean, how many boreholes and would
yeah,
they
I
typically?
can explain this to you. So roughly, rule of thumb, we would say, but that depends on the geology. You are looking at one borehole at 100 meters for 5 kilowatt of heat output. So that is, if we're talking small domestic property, 12 to 15 kilowatts heat demand, and the boreholes are mainly calculated based on or heat pumps are sized for the heat demand. You don't add with the domestic property with the boiler, you don't add heating demand, and then you don't add hot water demand on top, and then it gives you the total demand for the boiler. With the heat pump systems, you size the boreholes for kilowatt heating demand of the heating system, and then of course you have to add the kilowatt demands throughout the year for the hot water, but that's just for the running hours of the system. But
Mhm.
yeah, so small property, 2 or 3 bedrooms might need 2 or 3 boreholes. New properties, might get away with 1 or 2. Very well insulated or almost passive houses.
Mhm.
Older properties, large state homes or kind of manor houses, you might be looking at 600, 700 meters of square meterage of the property. That depends on the insulation. So you can be 10, 15, 20 meters, 20 boreholes. So that is, we are talking about 60 to 100 kilowatt system.
Mhm.
And the commercial system we are talking about, that was, I think, about 1.5 megawatt system. That was large commercial site north of London. So they've already done TRT test.
Mhm.
So we know now what it's going to, and what actually the geology is going to be like. And based on that, later they are designing their system based on the heat load demand, and then using the information from the thermal response test, they kind of utilizing this to make the bore field as efficient and suitable for the site to kind of maintain the output of the boreholes for many years to come. Because you can design the boreholes and they will perform really well for first 2 3 years, but they will over extract, and then in next years they will the efficiency will drop and drop. So then let's say extraction rates from 30 watts per meter, let's say, will drop down to 28, 25, and it will carry on dropping. So they don't fail straight away, but if they are not designed for the longevity of the system, they over time you might lose the performance of the system, and you might need more more electric to run the heating system, and you would then get less, and you get extract less from the borehole. So then you compensate with the electricity to generate the same, let's say, 15 or 20 kilowatts heating output.
Okay. But you're typically designing these so that those performance losses are minimized.
Yeah, so normal kind of designs are based on about 20 years kind of life, not lifetime, but initially the boreholes will work better on but after 20 years period, they should then kind of plateau and kind of stay like that forever, unless you start adding, or nearby sites will start extracting water, or somebody else nearby will start extracting more energy. But yeah, otherwise the design kind of normal MCA standards are to 20 years, and kind of that should kind of work absolutely fine.
Okay, cool. Okay, that might trigger some questions later on. Cool. Cheers,
No
Tom.
problem. Okay, so here you can see kind of those are few systems. We as a company can monitor some of our systems that we've installed over the years. So here we kind of showed you different systems, from large system, 15 kilowatts, 44, yeah, some small domestic, some large domestic. So you can see in some of them, you can see the efficiency drops or kind of comes from 4.61 COP, which is for every kilowatt of energy used of electric, you generate 4.61 kilowatt of heat output. So some of our system, you can see, is working at 8.6 for COP, which is really good. The boreholes are really well saturated. The client is not heating all the time at the house, so his efficiency is really great. But yeah, normally you would say our efficiency would be kind of around 4.5 to 5 mark, kind of on a, that would be a good system, good efficiency of the system. But of course, the efficiency drops when the heat pump is generating hot water, because you are heating the hot water cylinder to slightly higher temperature. So you have to kind of boost the temperature coming from the boreholes to 50, 52 degrees. But when you are heating the house, or normally the systems with the heat pumps are weather compensated. So you are measuring what's going on outside on regular basis, and the heat pump has programmed heat curve, which then adjust the flow temperature going into your heating system. So if today is 10 degrees or 15 degrees outside, heat pump will look into the curve that's been programmed inside and will say, today at 15 degrees outside, we only need to generate 28 degrees in the buffer tank. So the heat pump will maintain 28 degrees in the buffer tank. If some rooms in the house are calling for heat, they will draw this 28 degrees from the buffer tank, deliver this to the house. The buffer tank will drop temperature, and then heat pump, after some time when the temperature drops by some numbers, will then kick in again to try to maintain or top up their buffer tank to 28 degrees. Heat pumps are not running like boilers all the time, on off, on off. Otherwise, you will kill the compressor too quick. So there are certain parameters which are set in the hot water cylinder and a buffer tank. So the heat pump will wait for the temperature to drop by, let's say, in the buffer tank by, let's say, 5 to 10 degrees. So it's not starting all the time. So it says today, 15 degrees outside, let's maintain the temperature in the buffer tank of 28. It will wait for the temperature to drop to, let's say, 23. When the temperature drops to 23, the heat pump will start again, warmed up the buffer tank to 28, and will switch off. Then it will look what's going on in a hot water cylinder. Temperature in the cylinder is set to 52. It will drop, let's say, to 47, which is delta T of 5. You can say, okay, now we've dropped by 5 degrees. I will top up the hot water cylinder to 52, and it will then wait and constantly monitors the temperature in those two tanks and outside temperature. Overnight, then the heat curve will go slightly higher, so it will generate a bit more. And the best system are working being heated all the time. So you don't switch off the heating system in a house overnight or reduce the temperature in a house overnight, unless somebody likes slightly cooler bedrooms than air, that's fine. But we've noticed that the efficiency is much higher if you just leave the thermostats in the living room area, 21 degrees, bedrooms 18, kind of rooms like the design temperatures, and just let them kind of control themselves. Don't switch off at between 9 and 6 in the morning and then put it back on between 6 in the evening and, I don't know, 10 in the evening, and drop again after 10 a.m. till 6 o'clock in the morning. Those systems are then cycling, also because the heat pumps are measuring the temperature in the morning. When the system is trying to run, the system heat pump says, oh, it's 15 degrees or 10 degrees outside, I will only generate 35. House has cooled down overnight. Now the 35 degrees going into underfloor heating is taking a long time then to bring the house up to temperature, and much more energy if you are just trickling the heat all the time, 24 hours a day, a bit. So that's kind of how we found out they work better, especially in older properties or kind of, leaky with this kind of older windows, draftier properties. It's definitely much better to run like that. If I can just tell you about an example of the older property, client had got a listed building with big kind of thick walls, stone walls. They've got massive shutters on the inside, single glazing. They've done it as much as they could. They've installed underfloor heating in certain areas. they're aware that the house is never going to be kind of very hot, but they kind of didn't go ahead with replacing the radiators straight away. They said, we'll live in the house for the first year or first winter, and we'll see how the house is performing. But they've changed the way they are using the system. They are kind of controlling the system. So they put the thermostats and programmers to be on or available to generate heating 24 hours a day. And the house, just the whole structure of the building, the envelope of the house, just warms up and it retains the heat. And they decided not to upgrade any radiators. They are absolutely happy with those, and the house kind of stays at a nice steady temperature all the time. And they reduced the bills, running costs by, if I can tell you roughly, so the previous running costs were about £12,000 for the property, and they've dropped this down to, I think, about 4.5, 5K per year. So you can see the difference is quite significant.
And they're saying they're more comfortable in that.
And they're more comfortable. Yeah, the house is warm all the time, where before they were doing this old-fashioned way, switching on the heating system between 6 and 8. Then they were putting this off. Then they were putting this on at around lunchtime, and then they putting the heating on, in the evening between 6 and 10, and then then the house was cooling down. So now they just leave it as it is, and just the house stays like that. Of course, you're not heating the house all the time. The thermostat will monitor everything. The thermostats have got delta T built in them as well. So, if you've set the room temperature to 21, it will wait for the room to drop to 20 before the thermostat will say, okay, let's heat the room again. So, yeah.
And what was their motive for engaging you then? I mean, did they initially expect to make cost savings, or were they doing it because they were required, or they wanted to have
No,
a more
so they
environmentally
want
friendly solution?
a bit of everything. So that was a few years ago, when RHI was available. So they had quite a lot of funding from the government to install the system, but they were also concerned, and they kind of something was on his mind, that they want to do something more environmentally friendly. They were running on oil, and that's not the best use of fuel to use. They're quite wealthy people, so they wanted to be seen to do something right for the environment as well. But also, they've seen their running costs, and as it's okay, if we improve this, how are we going? Is it going to reduce our running costs? That was part of kind of all those aspects were kind of part of the big decision to go ahead and do this. And it's quite, we've done quite a few properties where clients are looking from energy saving costs and kind of the environmental impact it makes, and making this kind of, shall we do this or not? And that's the environmental thing is also a big part of this, because they are running oil. We do quite a lot of system in rural kind of areas where they don't have a gas, so they are running on oil. So yeah.
Cool. Okay, thank you.
So that's kind of about the efficiency and kind of how we suggest running the system. So here, I would like to mention about kind of few kind of myth-busting kind of issues, or kind of things we came across during our time. So a lot of clients are kind of thinking that, they need a huge amount of land to consider ground source heat pump. And again, you can see on this picture, the rig here is standing in the front drive. So you can see it's a semi-detached house with, some drive available in front of the house, but we were not able to access the back garden, which normally is bigger. So, but the client was determined. So here you can see the boreholes are drilled in the front garden. So here we had 3 boreholes in kind of triangle configuration. It was possible to do. Of course, there was a bit of disruption, because they had to later dig the drive to run the horizontal pipes to the garage where the plant room was later positioned. But there are ways of doing this. You can do deeper boreholes to reduce the number of boreholes. So we've done borehole where we had to actually move the rig with a crane over the wall to put this into the rear of the property, because there was no other way. And instead of doing 2 boreholes, because the garden was quite small, there was we've considered that it will be better, safer, just to drill 200-meter borehole, which then would provide them enough energy. So, yeah, that's kind of, it's really should be considered on a case by case basis. So that's not, with horizontal collectors, yes, that's definitely require that those kind of projects definitely require much more space, because you would need hundreds and hundreds of meters of horizontal trenches to provide you with the same amount of output. So yeah, those are definitely require much more space.
And then here, Tom, what was their motive then? I mean, you said he was determined. What was the rationale for him?
Here, the client wanted to remove oil, and they want to do something for the environment. They were really up for the kind of, and that was the main kind of purpose to do this, to reduce the fossil fuel usage and become more efficient and more, environmentally friendly. Because this client, and that was after the RHI disappeared, and there is now currently bus grant. I'm not sure if you're aware, which only provides £7,500 for their air source heat pump install and ground source heat pump. So there is no different kind of the amounts for the grant for both systems are the same. But yeah, they decided that they wanted something more efficient, and so they installed a heat pump at the back of the garage. So that was kind of the easiest way to do it, to bring the two pipes from the manifold to the garage. But yeah, that was their main kind of drive, was to be more environmentally friendly. And they said, we're going to live in the house for quite some time, so that's also going to reduce our bill running costs. So kind of, they consider this as well.
Yeah. Sorry, I will let you get on, but
That's fine.
Julian's made a point where he said he's had an air source heat pump for more than 4 years, and he really rates it. And he said it used to be that ground source heat pumps were more efficient than air source heat pumps, and that might be coming up in one of the myths, but they're pretty similar now. So from a business perspective, or from our perspective and house designers' perspective, is there a typical customer that and a preferred market that you operate? I'm assuming, obviously, from a business perspective, you're looking at the larger, more commercial gigs. But in terms of residential, and obviously you've just shown that you don't need a huge amount of land for ground source heat pumps. But at what point does it cross over where an air source heat pump becomes probably the better, more appropriate choice?
Well, if you don't have a space for the drilling, then there is no option. But yeah, the better solution we then to use the air source heat pump. I still wouldn't agree with this. I can understand what Julian's saying. They are more efficient now, or the efficiency of the air source heat pump is better than it used to be because of the refrigerant and stuff like that. But there is still a gap between the efficiency of the ground source heat pump and air source heat pump. So, it will probably be better than running this on oil or something like that. Efficiency is still better, but you are still not going to beat a ground source heat pump with air source heat pump. Let's say when it's -2 degrees or -3 degrees outside for a few days, when you are extracting the heat from the air, which is at -2 or 0 or something like that, and where the heat pump is extracting the heat from the ground, which is at 10 degrees. So that is in the summer. Air source heat pump, yes, summer, kind of spring, their efficiency is absolutely fine. But when it comes to the winter, when you're extracting the heat from the colder air, the efficiency then drops. So they're very good. I wouldn't say, if I was going to have something, I would consider air source heat pump out. We sometimes offer this to the clients because they're saying, no, it's too expensive. So I said, okay, if you are still considering kind of renewable system, why, would you consider air source heat pump? They're still good. They're still not, the efficiency is still not the same. So that I'm going to fight for this. So yeah, I can share with them some, if you look at the technical data of the air source heat pump and ground source heat pump, when the temperature outside is at 0, -2, -7, the air source heat pump efficiency dropped, and that's In the summer, yes, it kind of moves into the other side, but overall, still efficiency-wise, the ground source heat pump is still winning.
Cool. Okay, thank you.
But the other thing was people are thinking that you are extracting the heat that's coming from the boreholes is actually going into their house. And they say, okay, the ground is like 13, 14 degrees. How is it going to warm up the house? That's not the case. You know, we are using the heat to provide the energy to the heat pump, which is then extracted, and then it's boosted to 45 for central heating or 50 to your hot water. So that's kind of some of the people, I know some of our clients like, how does it work? And, you know, we're not drilling, you know, 1 mile down into the core where we can generate, you know, 70 or something like that. You're only going to see 10, 11 degrees, which is, but that's just a kind of educational thing that kind of, you know, people don't understand. About heat pump work in a cold climate, like, you know, here people are thinking, oh, you know, my house is not going to be warm enough in a winter. Hold on. The heat pumps were invented in Scandinavian countries, or kind of, you know, big manufacturers are based in Sweden, Denmark, and over there, this is very common system to use, and it's colder climate, and they're working absolutely fine. So yeah, again, that is just educational kind of aspect, and also making sure that systems are sized correctly. We've had an experience with lots of systems where boreholes or horizontal collectors were undersized, and then heat pumps are not performing and they are using a lot of electric, and clients are saying, I would like to rip it out because it's costing me too much to run, and you know, the heat pump is faulty or it's heat pump's fault. It's not heat pump's fault that it's not running. You know, if you install 13 kilowatt heat pump and your heat loss of the property is 20, the heat pump has no chance to deliver this. It will work very hard, will run all the time, over extract the heat from the boreholes because the boreholes have got certain running hours built in them. And the more you run them, the less energy you can extract from them, because it's like, you know, you are extracting this all the time for prolonged period of time. So yeah, that's kind of, there's a lot of there's the importance of the design is very high to make sure that the systems are meeting all the criteria to meet the, you know, heat load of the house and demand for the property. And some of our clients asking us, are we going to run out of the heat from the boreholes? And it says, you know, kind of, that's what I've explained earlier. You are designing this for, you know, longer period of time. We've worked with MCS tables and look into geology. We've got some calculators and formulas which are looking into this. You're also looking at running hours of the system. So you don't want the system to run for, let's say, continuous time for, I don't know, 30 hours or all the time, because the more you extract, if you're running the system for a long period of time, it will over extract the heat, and then it takes longer for the heat to kind of recharge. So if you look at the traditional house, you are extracting the heat kind of autumn, winter, and then spring, but then the systems really slows down in the summer, and then you're only still extracting some heat, but you're extracting purely or mainly to generate hot water. So the extraction rate drops. So that's when the borehole field have got time to recharge and bring the energy or the temperature back to the kind of the area. So that's how you are saying. So if you are designing, for example, system with heating for the house, hot water, and then you've got outdoor swimming pool. So in this case, you will extract the heat during the winter for the heating, and the hot water, and then in the summer the boreholes are not resting, because then you are extracting heat. You are then starting quite a heavy demand to heat your outdoor swimming pool. So in this case, the kind of running hours of the systems are very important, because if you then switch on your pool heating, the boreholes don't have the rest time. I don't have the time to recover and recharge. you are then extracting too much heat, and that's when they are losing their efficiency. So the running hours of the system then has to be taken into consideration if you are heating the pool, indoor or outdoor swimming pool, especially outdoor, because it kind of takes a quite big energy hits in the kind of spring when you start heating this from 5 degrees to bring this up to 30, and they're outdoor. Some people are not putting the covers on them, and they are losing quite a lot of heat. So yeah, it's all part of their design. Some clients are thinking that they're only suitable for the new properties. Again, that's not the case. It is part of the design, how well the property is insulated. Of course, in some properties you might need to use bivalent system where, yes, at certain temperature outside, the heat pumps might not generate enough heat output to provide required energy to the property and to keep this warm. So, you might consider, that's part of the design and calculations, that at some point, at certain degrees outside, you might consider help with a backup boiler or something like that. But it's all in the design, as I said earlier. But yeah, it's based on the case by case. And we've had a few clients asking about, is my hot water in the shower going to be hot enough? And I always kind of explain this way. We will generate the hot water to about 50 degrees. You might have to blend this with less cold water to work at kind of to give you enough or kind of the right temperature in the shower. But I always say, if you think about this, when you go to the hotel at 38 degrees roughly, you have to press the safety button to generate hot water. So at 38, you kind of go into the higher water temperature. So kind of people can see, how often do I go much higher than this? And I'm saying, okay, and we are generating 50. So if you really like hot water, you will just blend less hot water with the cold water to give you really hot water. And also with the ground source heat pump, depending on how many people is going to occupy the house and how large is the property, how many bathrooms they are, we will normally oversize the hot water cylinder to give you the more capacity in the cylinder for the heat pump, for the hot water. So that's kind of how you can compensate for the slightly lower water temperature in the hot water cylinder.
Cool.
So the next thing we wanted to kind of mention is about the deeper geothermal drilling. So I don't know if you know, if we are drilling 100 or 200 meter boreholes, they're not really getting that kind of heat from the core. So that really starts more at kind of 250, 300 meters, where you get that flux from the core of the earth, and that kind of provides that additional or kind of extra energy, which can improve the efficiency of the system. So in larger kind of projects where, commercial systems, this is kind of being considered quite a lot to reduce the number of boreholes or improve the efficiency of the boreholes. The boreholes are calculated or designed to slightly higher depth. We're talking 250, 30 meters or even more. Some of our drilling rigs can drill to 300 meters. That's not what we do very often, but we've done 250 and meter boreholes. But yeah, that is kind of, it kind of comes with a bit more risk about the boreholes collapsing. But again, it might be slightly more expensive, but in the long run, that will kind of provide better performance of the system. And again, you can reduce the borehole depth. And here you've got different applications. So kind of here, I will just quickly go through this. You've probably seen this. You've got domestic system, and they are all very similar. You've got heat pump, hot water cylinder, buffer tank. So that's kind of the normal setup in the plant room. So you've got always additional almost always, additional buffer tank, which stores the heat for the central heating. So that's kind of set up for domestic system. Here you can see kind of different installations where you've got larger residential property. This property, for example, had 33 boreholes, and you can see larger manifolds, which kind of you can almost walk into this as a chamber, and you can adjust the flow into each probe. And yeah, so larger units, three-phase units, suitable for large older properties, school, hospitals, other commercial properties. And here you can see that's what I mentioned earlier. It's like a bivalent or hybrid system where you've got the boiler in between those two cylinders, which can then provide backup or also provide a heating and hot water instead of the heat pump in case of the temperature outside drops too low or the property has too high heat losses for the system. The other option is district heating, and there are two versions. You can have a system where you are you've got a shared borehole array, and then you are installing flow and return with the glycol to each individual apartment or flat or commercial unit. And in commercial unit, you have a actual heat pump generating heat and hot water. Or you might have, let's say, instead of array 1 here on this drawing, you might have a energy center, where then you are generating heating and hot water in this energy center, and then you are providing this into different houses or something like that. So we've done a few systems like that where we are heating few houses from one energy center. Of course, you need to provide suitable pipes to distribute the high temperature hot water, but that's part of the design. More common now, cooling. So that is becoming now quite popular with large residential, high-end residential properties. You can do two versions: passive cooling, where you are using you are not engaging compressor, you are just transferring the heat from the property into the boreholes, and it's called passive cooling. So you can then use, let's say, underfloor heating to gently distribute that kind of cooling energy. It's not as efficient, but it provides some kind of cooling capacity. Or active cooling, where you actually use a compressor to extract the heat from your cooling system, and it moves the heat to, let's say, heating buffer tank, or can heat your swimming pool or any other area that you might need heated. Or if there is an excess of energy and the heat pump cannot utilize this, it will then discharge that excess energy into the borehole. So that's called active cooling. With a heating system, with the heating and cooling, kind of the design of the borehole is very important, because if the cooling demand is higher, you might need to then oversize the array to be able to cope with this extra energy you are trying to discharge into geology. And then important, the geology, type of the geology is very important to be able to then take that. And ground source heat pump as a long-term assets. So it's a long-term investment. Boreholes can last a long time. So the pipes will last 50 to 100 years. That's, they've got minimal degradation. They're not exposed to UV. And you are future-proofing their developments. You can expand the systems if you know that you are going to kind of increase the size of the property, and they are adding values to the property and reducing operating costs, and of course reducing carbon emission. And they work really well in combination with the PV panels. So lots of clients are now kind of putting PV panels, because your main energy consumption is from electric, because the heat pumps are running on electric. So clients are putting PV panels then to compensate that increased running of electric, or usage of electric.
Mm. And then what's a typical cost of installation cost for a borehole?
So
how does that work? I mean, we know how much air source heat pump costs roughly.
So it will be, you are probably looking at maybe 50. Ground source heat pump will be almost twice the price of the air source heat pump. Maybe not exactly, but you've got The drilling part is quite expensive because you've got a drilling, you've got to do header works, you need to then do the trenching to connect the boreholes together. So yeah, it is. I'm not going to lie. I'm not going to be able to make any magic numbers to
No.
say yes, we can make them the same price. There's unfortunately the cost of the drilling is still quite high. So if you are looking at small domestic property, 2, 3 boreholes, you're looking between 50K. Of course, you'll be able to claim the BAS grant, which is £7,500. But yeah, there is still some gap between the cost of the air source and ground source. So that's kind of everything what I can say. You can see what I've got here. If anybody's got any questions about something, are the boreholes visible? They're not. They will disappear meter below the ground. So you will see only manifold chamber flash in the ground, which you need to have an access to for the servicing to check the flow through each borehole every year during servicing. What's the benefit of drilling boreholes rather than doing horizontal trenching? With boreholes, you can build something on top. So we've done several projects, for example, in London, where we drill the boreholes at the ground level, then builders excavated, let's say, 2 levels down, and the boreholes are now currently under the building, which because you don't have an amount of space. With horizontal collectors, we would recommend not doing anything on top. So putting any roads, putting any buildings or sheds or warehouses on top wouldn't reduce their actually energy input from the rain, sun, and stuff like that. So that's then reducing their efficiency. But the efficiency anyway from between the boreholes and the ground and horizontal collectors are much. It's probably third of 1 meter of borehole will require about 3 meters of horizontal collectors, roughly. So you can see the efficiency drops. And depths are determined by the geology and heat demand of the property. Do I need to have a separate heating system as a backup? On smaller domestic properties, majority of the heat pumps that we are, for example, are using, they've got built-in immersion in the heat pumps. We also install immersions in the hot water cylinder as a double backup for the hot water. Larger commercial properties, that is really down to the client. We work with good manufacturers, so we've got good backup. So we kind of don't recommend doing this, but it's entirely client's choice. Depends really what the site is. If it's hospital or something, like we've done gallery where they want, we've got arts and stuff like that, paintings which need to have a certain humidity and temperature all the time. They don't want any kind of points where the system is not running and something happened to the artwork. They're not noisy. They're very quiet. New heat pumps are very quiet. They're inverter driven. Sometimes you have to put your hands on them to actually hear them running. So yeah, it is in comparison, you will not hear them probably if they're in a cupboard or in a utility room when they are running. And as for the radiators, do they need upgrading? As I said earlier, in some cases, yes, they might need to be upgraded if they are especially old and or thin or single panels. But with some of our clients, we said, just leave them, see how you get on, and then later you might want to upgrade them.
We had a session last week. We've had a couple of sessions actually, that the whole conversation around fabric first or not. And from a climate perspective, last week Nigel Banks from Octopus, he was saying, it's they're looking to get it's electrification over fabric is better, is going to get us there quicker. And yeah, you can upgrade later, but ultimately you're looking to electrify now as much as possible. So, Mario, similar questions really. What type of heating devices do you use in the apartments with ground source heat pump? It could be anything, couldn't it? I mean, it's just
Yep. So we have had clients who are using their fan radiators, so because they can reduce then the temperature of the system, so that
Hmm.
improves the efficiency. But that depends. My advice to the clients is, if there is an option to do any upgrades in the construction of the building, provide a cavity insulation, loft insulation, I would always suggest to do this first, because that will reduce the size of the heat pump system required. That will reduce the running cost of the system, and also they will reduce this cost of the system. Because if you think about this, if you upgrade the, I don't know, cavity insulation and loft insulation, and you reduce the total heat demand of the system by significant number, you're then reducing the number of boreholes required, the size of the
Hmm.
heat pump, and then it's reducing your kind of ongoing running cost.
Yeah.
And if you do this now and you suddenly install 20 kilowatt system, and then you do the cavity wall insulation later and stuff like that, of course your efficiency will improve and running costs will drop, but you initially spend for 4 boreholes and slightly bigger heat pump, where you could install, let's say, smaller heat pump with 3 boreholes. So, and that's,
Yeah. Yeah. Tom, we're just coming up to the end of the time,
Yep.
actually. I might just refer to Julian's point. He was in sort of more of a broader point. He was talking about how he went to Iceland a couple of weeks ago and he saw their thermal energy power plants, which provide 100% of electricity for Reykjavik and majority for heat energy. Do you know from what you're doing, are those types of technologies being explored here in the UK? Is it something that, I mean, obviously we're sort
What
of district heating, but how
the
large are these things going to get?
district heating, yes, that's becoming more and more common using, let's say, heat pump. There are also combined heat and power heat pumps. So they're generating electric and they're using the heat pump kind of compressor and stuff like that to generate the heat and generate the power at the same time. We've been designing one system. It hasn't come to kind of finalization yet, so it's not live project. It was big new developments with block of flats, 10 stories, where they were going to have energy center in the basement of each block of flats. And they were going to use the CHP units and heat pumps and stuff like that. So there was kind of combination of different
Hmm.
technologies to kind of generate electric and heat.
Okay, cool. Okay. Is there anything that, sorry, you just wanted to finish up with, like share your
Uh,
details?
no, I just wanted to could show you some case studies, but they're different system. We've talked about them
Yeah.
kind of while we're talking, so I'm not going to bore you. Just you can see different systems. So this is system. You can see design of the system in 3D, and then here you can see that system in actual plant room. So that's large domestic property with heating, passive cooling, and they had a outbuilding where the plant room was, and that was kind of quite away from the property in kind of new created plant room. So you can see they don't have to be in a plant in actual building. They
Hmm.
can be away from the building on the large properties. Yeah, that's it.
No, thank you very much. No, very interesting, very informative. So it was good to have a session on ground source heat pumps. Like I said, we haven't had one for well over a year, so I appreciate that, and generated lots of questions from the guys as well. So thanks everyone. Thanks for taking your time, Tom.
No problem.
Yeah,
Thank
thanks
you.
for sparing some time during your day to talk with us. I'll share the presentation on Mech's work along with the recording, and I'll share it with you as well, obviously, Tom. So yeah, have a
Perfect.
good
Thank
day,
you.
everyone, and enjoy your summers, and we'll speak soon. Cheers, guys.
Thank you. Bye.
Bye.